Okay, we're going to start on page 14 of your notes packet. So we're finishing up section 3.4, actually, not 3.5. We didn't get to finish this part in class, so I want to make sure we get it filled in. So go ahead and turn to page 14. So in this section, we just have this equation that gives us the relationship between density and molar mass. So really the equation, we just kind of need to know what everything in here stands for. So the M in this equation represents our molar mass. And this is basically like using what we know about gas laws and pressure and temperature. We can use that if we also know the density to determine the molar mass of a substance and figure out what that substance is. So molar mass is in grams per mole. And we have our D in this equation is going to represent density. Now, the tricky thing about density here is that it's going to be in grams per liter. The reason for that has to do with our R value, which I'll talk about here in just a second. Normally, we deal with density in grams per milliliter, but because of our gas constant, remember R from our ideal gas law is 0.08206. And the units for that are atmospheres times liters over mole Kelvin. So since that's in liters, we also need our density to have units of liters. T is going to be our temperature in Kelvin, of course, and P representing our pressure. That pressure needs to be in atmospheres. So all the units that we're plugging in here, we need to make sure that we match our units for our R value. Okay, so let's go ahead and do this example real quick. So what is the density of NO2 gas at 25 degrees Celsius, 2.56 atmospheres? So first of all, when I see 25 degrees Celsius, I realize that needs to be 298 Kelvin. And if my molar mass is, sometimes when we try and remember this equation, if you just remember dirt on the top and then pressure on the bottom. So I need to rearrange this equation to solve for density, since that's what I'm looking for. Density is going to be equal to my molar mass times the pressure, which is given, over RT. From there, we can just go ahead and plug it in. And since they gave us the formula of the gas, we can figure out what the molar mass is. We can just add nitrogen and oxygen together, and we get 30.01 grams per mole. So we can then go ahead and just plug that in to calculate density. So 30.01 for my mass, my pressure is 2.56. R, my constant, 0.08206, and then 298 Kelvin. Okay, that's going to give me a density of 3.14. Main thing is just to remember that that's in grams per liter. So in this next section, 3.5, we're basically going to be looking at the relationship between three things. The kinetic energy, of the molecules. So we're going to be talking about gas molecules. These are all comparing gas molecules. How much energy do they have? How much mass do they have? And then what is their velocity? So in physics, you use this equation to calculate kinetic energy of different objects. Here we're going to be talking about the energy specifically for molecules. So big idea right here. If the temperature is the same, remember that temperature is a measurement of kinetic energy. So if two molecules have the same temperature, they also have the same kinetic energy, okay? So that's a really big idea, and they always try and trick you with this on the test. So they'll ask you things like, they'll give you all kinds of information and all kinds of numbers, and but really, if it's the same temperature, you just have to recognize that and know that the kinetic energy is the same. So over here on the right, it says equal amounts of moles of N2 and O2 are both at STP. So let's just remember, first of all, that STP, standard temperature and pressure, is 273 Kelvin. and 1 atmosphere of pressure. But the only thing that matters here for this question, which sample has more kinetic energy? They're going to have the same kinetic energy because they're both at STP. If they're at the same temperature, it doesn't matter what the molecules are. It doesn't matter what their masses are. Their kinetic energies are going to be the same if they're at the same temperature. Okay, this question right here, we'll get back to because we need to talk about velocity, which is different than kinetic energy. So here we're going to have molecules that we have to compare the speed for, or the velocity. So velocity is how fast they're traveling. They still have the same temperature. Okay, so if they have the same temperature, they have the same kinetic energy, but it doesn't mean that they have the same velocity because kinetic energy has to do with velocity and mass both. So what you guys need to know basically is if you're comparing which ones have the same or which ones have different velocities, you have to know that the lighter molecules are going to move faster. That makes sense. It's easier for lighter things to move than it is for heavier things to move. So going back to our previous page, when we had N2 and O2, so the molar mass of N2 is 28 grams per mole, and oxygen has a mass of 32 grams per mole. And the question is, which one is going to have the higher average molecular speed? That's going to be nitrogen because lighter molecules move faster. So that kind of applies to these next two things, diffusion and effusion. Diffusion is just kind of the spreading out of gases throughout their container. They don't just all stay put in one place. Effusion would be like if you have like a hole in your container, like you get a hole in your tire and the gas in your tire slowly leaks out over time. They're going to have different rates of effusion based on the masses of the molecules again. And it's similar, these two ideas go together. So lower molar masses, things that are lighter, they're going to leak out of the holes in the container faster than heavier gases. So over on the right side, it says consider equimolar. That's like, they really like to use this word to mean equal amounts of moles. So I have equal amounts of moles of hydrogen, nitrogen, and fluorine placed in a container, has a pinhole opening. So just kind of picture we've got a container, it's got H2 in here, it's got N2, and it's got F2. And then there's a little hole in the container, and the gases are going to be able to like leak out of that little hole, okay? So it says after some time has passed, place the gases in order of increasing amount remaining in the container. So what you need to know is that the lighter things are going to leak out faster, okay? So what I'm going to have the least of over time is going to be hydrogen, because hydrogen is the lightest, so it's going to leak out the fastest. What I'm going to have most left over in the container is going to be the heaviest, which is going to be fluorine. Okay, in this next example, we have HBr, and HBr has a molar mass of 81 grams per mole, and NH3 has a mass of 17 grams per mole. Okay, so the question says, two gases are placed at either end of a tube at room temperature as shown. When they meet, a white-yellow precipitate will form. Where in the tube do you predict to see the precipitate? They're basically saying, okay, this little cotton ball right here is soaked with a liquid that's going to evaporate. And as it evaporates, it's going to travel inward in the tube. This is soaked with the liquid that's going to evaporate, and it's going to go in that direction. So we have to figure out where they're going to meet. So basically what I need to figure out is I need to figure out, since NH3 is lighter, it's going to move faster. HBr is heavier, so it's going to move slower. So what's going to happen is when they meet each other, HBr is not going to be able to travel as far as the NH3 will in that same amount of time. So basically, I mean, you're not supposed to be able to calculate exactly where that is, but you just need to be able to identify they're going to meet somewhere closer to HBr because HBr travels slower in that amount of time. So in our next section, we're going to look at these Maxwell-Boltzmann diagrams. And our Maxwell-Boltzmann diagrams basically are going to show us the behavior of gas molecules at different temperatures. So, well, there's actually two different situations. So looking at our models over on the right, we'll look at a graph that shows helium, so the same element at different temperatures. And then we also can have a graph where the temperature is the same, but they're different molecules. And basically what it represents is it represents the average velocity. So this right here represents our average velocities of all of the gas molecules that are in that sample. Okay, the area under the curve represents the total number of molecules. So if I'm looking at just one curve, and so it looks something like this. Okay, the area under the curve is going to represent the total number of molecules of that particular gas sample. The peak of each curve represents basically the average velocity. Those two things go together. So when I'm looking at my graphs over here to the right, so I have this is a peak, this is a peak, this is a peak. And on my x-axis, it shows me particle speed. So wherever that peak is on my graph represents the average velocity. So what that means is that if this is helium all at different temperatures, the farther to the right the peak is, the faster those molecules are moving. So that's really kind of what you want to focus on, is the peak of the graph. The farther it is to the left, it's not how tall they are. Okay, the tallness of the peak represents how many molecules have that speed. But you want to tell how far left or to the right those peaks are. The farther to the left, the slower it is. And the farther to the right, the faster it is. So molecules with a greater velocity have peaks farther to the right. And those would represent our molecules that are at a higher temperature. So you'll be given graphs and it'll say, you know, which graph represents the gas that's at the higher temperature. And it won't have like the labels on the side. It'll ask you just to identify it. So if you know that faster things or molecules move faster at higher temperatures, then you'll pick the one with the peak to the right. Slower is going to be the ones at the lower temperature. Okay, and for my second graph down here below, I've got, they're all the same temperature, so we have to look at it a little bit differently. If they're all at the same temperature, then the one that's farthest to the right, the peak that's farthest to the right, is still the one that's going to be moving faster, and the peak farthest to the left is still the one that's going to be moving slower. But it's going to be for a different reason because they're all at the same temperature. So it's not because of that. It has to do with their molar masses. So this graph is showing all of our noble gases. Helium is the lightest, so that means it's going to be moving the fastest. So that's going to be represented in my peak that's farthest to the right. Xenon is my heaviest, so it's going to be represented by the peak that's farthest to the left. So the main thing you need to know is faster things have peaks further to the right and slower things have peaks farther to the left. So the example down below is showing an old free response question that we've had before. So it says the graph below shows a distribution for the collision energies of reactant molecules at 120 degrees Celsius. Draw a second curve on the graph that shows the distribution for the energies at 30 degrees Celsius. Okay, so basically I need to look at that and I need to say, okay, this temperature represents 120 degrees Celsius. This has a lower temperature, 30 degrees. And if it's a lower temperature, it's going to be slower. And so that means my peak needs to be farther to the left. And the farther to the left my peak is, the higher it goes, because it all kind of gets like smushed over to the side. So you should draw something that has a peak farther to the left. And the other important thing about that, so let's go ahead and label that. So that would be 30 degrees Celsius, representing molecules that are moving slower. Let's see. The other thing we need to pay attention to here is that this line needs to go below this line right here. And the reason for that is because we have this little dashed line that represents activation energy. And so what this line is telling me is everything that I have underneath the curve beyond that dotted line represents molecules with enough energy to react. But if it's at a lower temperature, we're going to have less molecules that have enough energy for a reaction to take place, less molecules that have the right amount of activation energy. So that line needs to go down below right there. Okay, over here on the right real quick, just since we're here, on the graph below, draw a curve that represents a gas with a smaller molar mass. Smaller molar mass means lighter. Lighter means faster. So my peak needs to be farther to the right. And if my peak is farther to the right, it's not as tall. Okay, so you should have a curve that looks like that. So this is the last slide that we're going to go over, and then we'll be done. We'll go over the other stuff another day, but this section is deviations from ideal gas behavior. So basically what we've been doing so far is we've been just pretending like everything follows the ideal gas law, right? So the ideal gas law is PV equals nRT, and basically we're pretending like everything follows that rule all the time. But of course we know that nothing happens perfectly all the time. So we need to know just some general things about when gases don't behave the way they're supposed to. So one general rule, the stronger the intermolecular forces are, the more they deviate from ideal behavior, okay? So basically, the closer molecules get to each other, the less they behave the way they're supposed to, okay? Fourth period, it's kind of like Mitchell and Jack. When they get closer to each other, they don't behave as well as if they're farther apart, or any other people that are like that. Anyways, okay, so real gases behave like ideal gases at high temperatures and low pressure. So real gases, okay, they're the most like ideal gases when they're far apart. And so if you just remember that they behave better when they're far apart, then you can think about, okay, high temperature, that means that they're going to be moving faster, so they'll be able to move farther apart from each other. Same thing with low pressure, the molecules will be able to spread farther apart. But where they deviate the most is when the molecules are close together. And when the molecules are close together, they bump into each other more, they don't do things the way they're supposed to. And so those conditions would be if we have gas molecules that are under high pressure, because then they're all squeezed like close together. Also low temperature, because the molecules slow down and they all kind of get close together. Okay, so there's two situations that they'll ask you specifically about on the AP test. So you'll get a situation where it'll say, hey, like according to the ideal gas law, this is supposed to happen, but the pressure is actually less than expected. And they want you to explain why. Okay, so if that's the case, your explanation needs to talk about intermolecular forces. So let's look at what that looks like. If we're talking about ideal gas behavior, maybe I have, my gas molecules are all kind of evenly spread out in the container. But if they have strong intermolecular forces, then those molecules will all be closer together. And if they're closer together, then they don't collide with the sides of the container as often. And collisions with the sides of the container is what causes pressure. So the stronger the intermolecular force is going to be, the lower the pressure is going to be. It'll be less than expected when we calculate using the ideal gas law. Okay, the other situation they'll say, okay, we calculated pressure and we know what it's supposed to be with the ideal gas law, but when we measure it, it's more than it's supposed to be. And why is that? Okay, so here's why. When we're talking about ideal gases, we are pretending that they're all the same size. But we know that not all molecules are actually the same size. So maybe my real gas molecules are a lot bigger and they take up more space. So if those molecules have a larger volume and take up more space, then they're going to create more pressure because they'll collide with the container walls more often and with more surface area as well. Okay, so two things. If the actual pressure is greater than it's supposed to be, it's because of volume. So you have to remember that those two things go together. And if the actual pressure is less than it's supposed to be, it's because of the intermolecular forces that are pulling the molecules in close together. Okay, so let's go over here to the right real quick. We'll just finish it up so that you have it all the way filled in. NO2, CO2 have similar molecular weight. Which gas would you predict to deviate from ideal behavior the most? Okay, NO2 has dipole-dipole forces holding them together. Carbon dioxide has London dispersion forces. So deviating the most from ideal behavior are going to be the ones that have stronger intermolecular forces. So NO2 is going to deviate more from ideal behavior. Okay, in my chart over here, circle the set of conditions for each of the following. So the most ideal is going to be low pressure, high temperature. The least ideal is going to be high pressure and low temperature. Okay, that's it for this, you guys. Go ahead and bring these notes back with you on Monday. We'll be doing an activity looking at those Maxwell-Boltzmann diagrams a little bit more and doing some practice problems with that. So I will see you guys in class on Monday. Have a great weekend.